Hello everyone. Since we are continuing with the chemical properties of alkyl halide, now we are going to focus on one of the most important properties or the chemical reactions of alkyl halide, that is nucleophilic substitution reaction and the elimination reaction, which is the most important reactions of alkyl halides. Now these alkyl halides are the most controversial compound of all the chemical compounds or the functional groups in organic chemistry. These alkyl halides simultaneously proceeds to a number of reactions, side or parallel reactions. The only thing is we can suppress one reaction and we can increase the quantity of another or the rate of another reaction. So today we are going to focus on the elimination reactions of alkyl halides. Now in elimination reactions, basically a group or an atom of groups of atom or a neutral molecule is completely removed without it being replaced by another group or groups of atoms. So when we remove a neutral molecule from this substance, this gives rise to alkenes or alkynes. So alkyl halides on elimination gives you alkene. So we are going to focus on the elimination reaction of alkyl halides. So the heading for today's discussion will be elimination reaction. Now these elimination reactions of alkyl halide can be visualized in three different mechanisms. Based on this, these elimination reactions are of three types: E2 type, E1CB type, and E1 type. So we have three different mechanisms proposed for elimination from alkyl halides. In all these elimination reactions, the final products will be alkene, but the mode of elimination of alkyl halide differs. Now this E2 mechanism, E1CB mechanism and E1 mechanism, the basic difference between these three mechanisms is based on the different timings for the breaking of carbon-hydrogen bond and the carbon-halogen bond. So during the course of elimination, N hydrogen halide HX is to be completely removed. So there are possibilities that by both carbon-hydrogen and carbon-halogen bond break simultaneously in a concerted state. Or the second possibility is carbon-hydrogen bond breaks first, followed by breaking of carbon-halogen bond. Or the third possibility is carbon-halogen bond breaks first, followed by carbon-hydrogen bond. So based on the difference in timing of this breaking of carbon-hydrogen, carbon-halogen bond, these are classified into three different pathways. These are the pathways. So this is based on different timings for breaking of carbon hydrogen and carbon halogen bond. Now, out of these three mechanisms, the most common mode of elimination given by alkyl halide is the E2. This is the most common pathway, and this E1CB pathway, this is the least common, and this E1 is in between E1CB and E2. Now in this E2 mechanism, E for elimination, 2, 1, 1, this stands for the molecularity of the reaction during the rate determining step. So E2 reaction, in this E2 reaction, carbon hydrogen bond and carbon halogen bond breaks simultaneously. So if carbon hydrogen and carbon halogen bond breaks simultaneously in the rate determining step, then that mechanism is known as, or that pathway is known as E2 pathway. So look at this, we have simultaneous breaking of carbon hydrogen carbon halogen bond in E2. Now in E1CB, carbon hydrogen bond breaks first, followed by carbon halogen bond. So in the second pathway, that is E1CB, first carbon hydrogen bond breaks, followed by carbon halogen bond. In E1's mechanism, carbon halogen bond breaks first, followed by carbon hydrogen. Followed by carbon hydrogen bond. So this is the basic difference between these three pathways of elimination. So we'll take up one by one. What are the basic features? And what is the intermediate kinetics, stereochemical evidence, factors affecting this rate of reaction, and the product formed. So first we'll take up the most common mode of elimination, that is E2 mechanism or E2 pathway. So let's start with this E2 pathway. Now again I'll cover all this in detail in each and every mechanism or pathway. So coming to E2, so let's start with the basic or the important features of this E2. So we have this E2 pathway. Important features of this E2 pathway. The word E, capital E, represents for elimination. Elimination. These two in the pathway represents elimination. Bimolecular, molecularity of the reaction is true. So if you look at this, these two represents the molecularity. So molecularity of the reaction is 2. So these two represents the molecularity of the reaction. So let me just remind you this. What is molecularity? We have gone through chemical kinetics. So during this chemical kinetics, we have discussed elementary reactions, means the one which is supposed to take place in the single step. Now, the number of molecules of the reactant which involves in product formation in the rate determining step of an elementary step reactions. So how many molecules participate in any elementary step reaction, that is known as molecularity. So when we take up this mechanism, the molecularity of the reaction means the number of molecules involved in this rate determining step, elementary step, is 2. So molecularity is 2. This E2 reaction, the kinetics of the reaction says rate of reaction is equals to rate constant K into concentration of alkyl halide and the concentration of base. So if you look at this, the rate of reaction is directly proportional to the concentration of base, and rate is first order with respect to base as well as first order with respect to alkyl halide. That means for this E2 reaction, the requirement is the rate becomes faster if we use a strong concentrated base. If the concentration of the base is less or we are using a weaker base, then the rate becomes slow. So E2 requires strong and concentrated base. That means for the same base, if we keep on changing the concentration, means increasing the concentration of the base, the rate becomes faster. So with the same base, if the concentration is increased from dilute solution to the concentrated solution, the rate becomes faster. So if you look at this rate of reaction or the kinetics of this reaction, the total order of reaction, look at this, alkyl halide first order, base first order. So total order of reaction is 2. So coincidentally, look at this, molecularity is also 2, order is also 2, but these 2 does not stand for the order of reaction. These 2 in the pathway stands for the molecularity of the reaction. E2 reaction occurs in concerted single step pathway. Occurs in a single step. So the number of steps involved in this E2 mechanism is single step. This reaction occurs in single step. So whenever reaction occurs in single step, we say this is concerted mechanism, concerted pathway. This E2 reaction occurs through a transition state formation. Transition states, TS. All E2 reaction occurs through a transition state. E2 reaction, the reactivity order of alkyl halide so look at this, we have this alkyl halide. Now in case of alkyl halide, we have different halides. So we have RF, RCl, RBI and RI, different alkyl halides. Look at this, alkyl group remains same but halogen different. If the alkyl group remains same or the halogen is different, then the reactivity order increases from fluoride to chloride, chloride to bromide, and bromide to iodide. So alkyl iodide is the most reactive and alkyl fluoride is the least reactive for this E2 pathway. If the alkyl group is different but the halogen is same, for the same halogen we can have primary halide, primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. If we have this, then the reactivity order is primary, secondary, tertiary. So with the same halogen, primary is less reactive than secondary, secondary is most reactive than tertiary. So look at this, the most reactive alkyl halide for this E2 mechanism is tertiary iodide, alkyl iodide. So tertiary alkyl iodide will give you the maximum yield, and the minimum yield of the alkene formed by this E2 will be from primary alkyl fluoride. In fact, alkyl fluoride does not undergo reaction by this E2. So this is the reactivity order of different halogens as well as different alkyl groups for this E2 pathway. Now in this E2 mechanism, as I told you, we are removing a neutral molecule and an alkene is developed. So the alkene formed will be governed by a rule which is known as Sage's rule. So orientation of elimination favors Sage's. That means more stable, more alkyl substituted alkenes will be forming as a major product. That is Sage's elimination product will be favored in normal E2 reaction. So we have this E2 reaction. Now for this E2 reaction, the preferred choice of solvent will be weakly polar aprotic solvent, because solvent plays a very important role in elimination reaction. So if we increase the polarity of the solvent, then the mechanism may shift from E2 to some other mechanism. So the most preferred choice of solvent for this E2 reaction is E2 reaction is favorable in weakly polar aprotic solvent. So these are some of the important features that we are going to discuss in this elimination by molecular pathway. Now all these features can be explained by when we take up the mechanism. So from this mechanism we can explain why this reaction में इतना features क्यों है. This reaction E2 reaction, this is also known as 1,2 elimination. I'll tell you what is the meaning of 1,2 elimination. 1,2 elimination or simply beta elimination. 1,2 elimination or beta elimination. This E2 reaction, this 1,2 means the living groups, that is hydrogen and halogen, are removing from 1 and 2 position. So since both the living groups are eliminating from 1,2 position or alpha beta position. So in older literature, alpha beta, the word alpha is removed and this is simply known as the beta elimination. So this is the meaning of 1,2 elimination or beta elimination. Now in this E2 mechanism, the leaving groups hydrogen and halogen from 1 and 2 position should be anti position or staggered position. Eliminating groups or the leaving groups. Leaving groups, that is hydrogen and halogen, should be anti or staggered position. Should be staggered position or anti position. Now we'll explain all this while taking out the mechanism again. Now in this elimination reaction, if hydrogen is replaced by deuterium, rate becomes slower, indicating that there is a direct breaking of carbon hydrogen bond in the rate determining step. In chemical analysis, this is what we call as primary kinetic isotope effect. Primary kinetic isotopic effect is observed, that is, if hydrogen is replaced by the deuterium D, then rate of reaction decreases, indicating the breaking of of carbon hydrogen bond in the rate determining step. So why carbon, when hydrogen is replaced by the rate of reaction decreases? Look at this. The bond strength of carbon hydrogen bond is less than carbon deuterium, which is less than carbon tritium. As the isotopic mass increases, the bond strength increases. Bond strength. So look at this. When we replace this hydrogen by deuterium, bond strength increases. If the bond strength increases, to break this carbon deuterium bond, more energy is required. Hence, the rate becomes slower. So this is what we call as primary kinetic isotope effect. So this is one of the methods which can is used for measuring the kinetics or the rate of reaction in kinetics measurement. So this is some of the important features that we often observe in this E2 pathway. Now, to explain all these things, we have to take up the mechanism part. So now let's come into the mechanism part of this reaction. So all these features can be easily explained from the mechanism. So let's discuss this mechanism part. Mechanism of E2. So we have to look at this alkyl halide. this carbon from which halogen is to be removed, this carbon is known as alpha carbon or 1 carbon. The carbon from which hydrogen is to be removed, this is known as beta carbon or this is known as 2 carbon. So since hydrogen and halogen, these are leaving from 1 and 2 positions, so this is known as 1,2 elimination or alpha beta elimination. So in order literature, this the word alpha is removed and simply known as the beta elimination. Now this is to be reacted with a strong concentrated base. This is base. Let me use this word B minus, which represents strong concentrated base. Now when this base, now look at this, since we are having a base, the role of base is to abstract acidic hydrogen. So whenever in a chemical reaction base is used, this base will always look for the acidic hydrogen. Now look at this. Halogen is electron withdrawing group. So when this withdraws electron density from carbon, carbon becomes electron deficient. So this carbon will withdraw electron density from second carbon, and this carbon will withdraw electron density from hydrogen. So this hydrogen is slightly acidic, not very acidic, so D requires a strong concentrated base. So base B minus will approach this acidic base, and this electron which was sharing between beta carbon and hydrogen is transferred between alpha beta carbon. When this electron is transferred to alpha beta carbon, valency of this alpha carbon increases, which is not possible. So finally this halogen has to leave the system with its electron pair. So if you look at this, all this process is taking place simultaneously in a concerted single step pathway. So during this course of reaction, a transition state is formed. So we have, look at this is sigma bond. Now in the transition state, alkene character is developed because this electron is transferred here, and this carbon halogen bond starts to break, and this carbon hydrogen bond also starts to break, and base hydrogen bond starts to formation. So there is a simultaneous formation of bond as well as breaking a bond. Since all this breaking and formation is taking simultaneously, so this is assumed to be in a concerted mechanism. So this particular state, this is what we call as transition state. So reaction is assumed to proceed via this formation of transition state. In the final step, base hydrogen bond forms a bond, carbon hydrogen bond breaks, carbon carbon double bond develops, and carbon halogen bond breaks, and the product form. This is the alkene that is formed, plus look at this, base forms a bond with hydrogen and X minus leave the system. So this is our product. Now coming to the features that we have discussed about this E2 pathway. Now first is E2, that is bimolecular, means two molecules are involved in the rate determination. This is a single step, so this is a rate determining step. Now look at this, what are the molecules involved? We have this alkyl halide and base. Both alkyl halide and base is involved in the rate determining step, hence the molecularity of the reaction is 2. Now reaction does not proceed in absence of this base, because for this requirement is we should have a strong concentrated base. So the rate of reaction changes as the nature and the concentration of base changes. Now coming to this transition state, now look at this. We have discussed earlier the leaving groups, hydrogen and the halogen, should be at a distance of 180. Why this NT position is required? We have to explain. In E2 mechanism, the leaving group, hydrogen and halogen, should be NT or staggered to each other. Why this is so? Now if you look at this particular transition stage appears alkene character develops. So look at this transition state aqueous alkene character. Now look at this. We have seen the molecular arrangement. We have eclipse form and we have stagger form. Now when discussing this molecular arrangement of groups in 11th chemistry, we have said stagger or NT form is more stable than the eclipse form. So since stagger being more stable is less energetic, so elimination is favored from the less energetic or the more stable NT form, so that the energy difference is reflected in the transition state. That means if the starting alkyl halide is more energetic, then the transition state will also be more energetic. If the transition state is more energetic, then its stability will be less. If the transition state stability is less, then chances for this reactant to convert into transition state will be less. If the transition state formation is less, then the rate of reaction will become much slower. So to increase the stability means this transition state should be less energetic. So for this to be less energetic or more stable, the requirement is the starting alkyl halide should be less energetic, more stable, stagger or NT form. So that energy difference will be reflected in the transition state. That means any factor which increases the stability of transition state will increase the rate of reaction. So to increase the stability of transition state, we have to use an alkyl halide in NT or staggered form. So this was the reason why the leaving group should be NT. I'll give you some other conditions also. The question is NT. Why NT to each other? First one, NT configuration is more stable. If NT configuration is more stable, then energy difference is reflected in the transition state, and hence its energy difference is reflected in the transition state. So if you are starting from low energy or less energy reactant, the transition state will also be less energetic, more stabilized. So this is one of the reason why we have to start from, or the leaving group should be NT to each other. Second reason why this group should be NT to each other. Now look at this. Base is approaching the reactant with an pair of electron. The leaving group is also leaving, that means CX, X minus is leaving the system with this electron pair. So if base is moving from this side and X minus is leaving from this side, so both having electron rich, so there is a chances for electron repulsion. So because of this electron repulsion, both this base and this leaving group should be trans or anti to each other, so that the electronic repulsion between the approaching base and the leaving group X minus is minimized. So if base is coming from this side, the leaving group is leaving from this side, so there is no, if they are at a distance of 180 degrees, so there is no chances for electron repulsion. So this is one of the requirement why approaching base and the leaving group should be trans or anti to each other. So if they are anti, then electronic repulsion between approaching B minus and leaving group X minus is minimized. So to avoid or to minimize the repulsion between the approaching base and the leaving group X minus, both these groups should be at a distance of 180 degrees, that is anti configuration. Now the third point, why this is to be anti. Now look at this, base is coming from this side and if this X minus is leaving from this side, again there is a chances for steric hindrance, collision हो सकता है. So अगर मैं बेस इधर से जाएंगे, X माइनस उधर से जाएंगे, then there is no chances for steric collision और collision का chances नहीं है, so steric hindrance is minimized. So to minimize the steric hindrance between the approaching base and the leaving group, again these two should be at a distance of 180 degree or anti position. So to avoid steric hindrance between base B minus and the leaving group X minus. So to avoid steric hindrance, to minimize repulsion between base and the leaving group X, these groups should be at a distance of 180 degree or anti or trans position. And when we have anti position, these stagger from being more stable, less energetic. This energy is reflected in the transition state, leading to more stabilization of transition state. So this is the reason why we have to have anti-elimination. Now next one, look at this transition state. In this transition state, 5 groups, that is base, beta hydrogen, beta carbon, alpha carbon and X. All these 5 groups should be in the same plane, that is anti-periplanar configuration. These groups. These 5 groups should be in the same plane. In the same plane. So this transition state in which these 5 groups should be in the same plane in anti position is known as anti-periplanar configuration. Anti-periplanar. So we have explained why this has to be anti. Now the question is why this group should be in the same plane. Why they should be in the same plane? Periplanar. That means same plane. Now we have to explain why this group should be in the same plane. Now let's see. During the course of reaction, there is simultaneous breaking of beta carbon beta hydrogen bond, formation of alpha beta multiple bond, breaking of alpha carbon and halogen bond. Now, as this beta carbon hydrogen bond breaks, there is a p orbital that is being developed, and as this alpha carbon and halogen bond breaks, again there is a p orbital that is developed. Now between these two alpha carbon and beta carbon there must be pi bond formation. So pi bond formation requires that the p orbitals should be planar. If the p orbitals are in the same plane or in the same direction, there is chances for pp overlap resulting in the formation of multiple or pi bond. If the developing p orbitals are not parallel to each other, then the question of pi bond formation does not take place. So the periplanarity is a requirement because the developing p orbitals in beta carbon and the alpha carbon as beta hydrogen and halogen bond breaks should be in the same plane, resulting in more effective or stronger pp overlap. So for this the requirement is this should be in planarity form. So the reason for this planarity is the developing p orbitals on alpha carbon and beta carbon will be in the same plane planar, that is parallel to each other. The developing p orbital on alpha carbon and beta carbon will be planar, that is parallel, resulting in more effective overlap for pi bond formation So this is the reason why this has to have anti-periplanar configuration. So as the developing pi orbitals, okay, this is alpha carbon, this is beta carbon. So developing p orbitals are in the same plane or both are parallel, then there is a tendency for this pi pp overlap resulting in stronger pi bond. If the developing p orbitals are perpendicular to each other or they are deviating from the planarity, then there is no question of pp overlap resulting in pi bond formation. So for this requirement is these groups should be in the same plane so that p orbitals are in planar and effective pi bond formation takes place. That means any factor which increases the transition state will lead to the increase in the rate of reaction. So the factors that increases the stability of alkene will also increase the stability of transition states. So I am repeating the sentence. Any factor that helps in stabilization of increase the stability of alkene will also increase the stability of transition state. The reason being, transition state already acquires alkene character. So those factors which helps in stabilization of alkene will also stabilize the transition state. The reason being developing of alkene character in the transition state. So this is anti-periplanar configuration. Now some other factors that I have discussed for this E2 mechanism is the reaction rate. We have discussed the rate of reaction. Rate of reaction, reactivity order of alkyl halides. Now look at this. While discussing the reactivity order of alkyl halide, alkyl iodide was the most reactive and alkyl fluoride was the least reactive. Now let's see why alkyl iodides are the most reactive for this E2 part. In the transition state, there is a breaking of CX bond. So if the CX bond is a stronger bond, tendency for its breaking will be less. If the tendency for breaking of CX bond is less, the rate becomes slower. Now in case of carbon halogen bond, as we have discussed in physical properties, so the longest carbon halogen bond is Ci bond. CF bond is the shortest bond, Ci bond is the longest bond. As Ci bond is the longest, Ci bond is the weakest, and this can be easily break in the transition state. So this is the reason why carbon iodine bond or the alkyl iodide was the most reactive, because the bond strength decreases from carbon fluorine to carbon iodine. So look at this. Carbon fluorine bond length, carbon chlorine, carbon bromine and carbon iodine. Bond length increases. As the bond length increases, bond strength decreases. So Ci being the weakest bond can be easily break in the transition. So this was the reason why alkyl iodide was the most reactive in the transition state. So this is the reason. So in the transition state, there is a simultaneous breaking of CX bond. So if the CX bond is weaker, which can be easily cleaved, and the transition state stability increases, alkene formation increases. Now, if halogen is same and alkyl groups are different, then we have explained tertiary alkyl group was the most reactive and the secondary primary was the least reactive. Again, now look at this. The reason being transition state acquires alkene character. So if the alkene contains more number of alkyl substitution, then the number of hyperconjugating structures will be more. As the number of hyperconjugating structures are more, then alkene becomes more stabilized. So look at this. If we have alkyl group, alkyl group, alkyl group, alkyl group, so number of alpha hydrogen will be more. If the number of alpha hydrogen is more, then number of hyperconjugating structures will be more. So this alkene will be more stabilized. So that factor will be reflected here. If we have alkyl substitution here, alkyl, then because of this alpha hydrogen, this double bond character will be more stabilized, as was the case in case of alkene. So this is the reason why tertiary alkyl iodides was the most reactive for this E2 pathway. Next, again we second, this E2 requires aprotic solvent or weakly polar solvent. If we use protic solvent, because reaction requires a base, and this base has to abstract this acidic hydrogen. If the solvent is protic, then that proton will react with base, because this proton is less acidic. If you are adding a protic solvent, means we are adding acidic hydrogen in the solvent, so that acidic hydrogen will react with this base, so no reaction takes place again. And look at this, solvent polarization is not required here. The reason being, look at this molecule, so transition state, there is no charge separation. Since there is no charge separation, we require a non-polar solvent. So since there is no charge separation in the transition state, so we require a non-polar or weakly polar solvent. So this was the reason why E2 reaction requires a protic solvent. So we cannot use a protic solvent in this E2 mechanism. So please be careful while choosing the solvent for this E2 reaction. Now coming to orientation of E2 reaction, let's explain some examples. So I hope the points discussed is clear to you. Now we'll take up examples, and from this example we'll explain the orientation factor. So orientation in E2. Orientation factor. So means if we have two types of beta hydrogen, then this may result in the formation of more than one alkenes. One should be given format as a major product, the other one should be format as a lesser product, minor product. So orientation is Saijev's versus Hoffman. So formation of more alkyl substituted product is known as Saijev's. Formation of less alkyl substituted product is known as Hoffman. More alkyl substituted alkene. Hoffman less alkyl substituted alkene. So we have a orientation competition between Saijev's and Hoffman. So look at this, take this example. CH3, CH2, CHI, CH. So look at this is alpha carbon. So we have look at this beta carbon. This is also beta carbon. Now look at this, we have two different types of beta carbon. Then there are two possible products that could be formed, and the possible products are, look at this, removal of beta prime, we get this CH3, CH double bond. So we have to remove HI from this. So either we can remove this. So if you remove this, so we require, look at this, alcoholic KOH. In most of the reaction we use this alcoholic KOH. Alcoholic KOH is a strong base, strong concentrated base. Don't use aqueous KOH. You have to use alcoholic KOH, which is a strong base. So if we remove this, then we get a double bond here, CH3, CH3, that is one product. Second is, we can also remove this product, remove this HI. If you remove this HI, there will be CH3, CH2, CH double bond, CH2. Now we have to compare the stability of these two alkanes. The one which is more stable will be forming as a major product, and the more stability of alkene is dependent on the number of hyperconjugable alpha hydrogens present. Now if you look at this, we have this alkyl substitution here. We have two alkyl substitution on this doubly bonded carbon, alpha to this, alpha to this. So we have two alkyl substituted, and both these contains 3 hydrogen, so 6 hyperconjugable alpha hydrogen. On the other side, look at this, there is no alpha hydrogen here, we have this. So the one having more alkyl substituted product will be the more stable, so we say this is Saijev's elimination product. The other one having less alkyl substitution is known as Hoffman elimination. So for a normal E2 reaction, the product always governs by the stability of alkene form, and this stability of alkene, the more stable alkene is forming as a major product, that is what we call as side F. So these side Fs will be forming as a major here, and this will be forming as a minor product. So let's take up some other examples also here. CH3, CCH3, say we have hydrogen, CH, Br, CH2, CH3. Let's use this alcoholic KOH. So look at this. This is alpha carbon, we have beta carbon, we have beta prime. So there are two beta hydrogen that can be removed. Either we remove from this side or from this side. So remove from this beta, we have this product CH3, CH3, double bond C, H, C, H2CH3. The other product is CH3, CH, CH3, CH, double bond CH, CH3. So if you look at this, which one is Sachs product, which one is Hoffman product? Take the first product, look at this, we have alkyl substitution, second alkyl substitution, third alkyl substitution. In the second product, we have one alkyl substitution, two alkyl substitution. So the one having more number of alkyl substitution will be forming as a major product. So this is major, that is Sachs product. The one having less number of alkyl substitution, that is forming as a minor product, and this is Hoffman elimination product. So for normal into reaction, please make sure okay, the product is more substituted alkene should be forming as a major product. The problem becomes clear if we take up some more problems here. Take this. So 1 bromo, 1 methyl cyclohexane. 1 bromo, 1 methyl cyclohexane. If this is to be treated with alcoholic KOH, now look at this. We have different types of beta hydrogen. Look at this. This is beta carbon. This is also beta carbon. Both are identical. So there are formation of two products. Remove from this beta hydrogen. This is beta. This is beta prime. So we have, look at this, double bond CH3. This is from beta prime plus CH2 double bond, so removing by beta hydrogen. So now we have to compare this, the stability of these two alkene. Take the first alkene. So look at this. This is one alkyl group. This is second alkyl group. Oh, sorry. Double bond position is different here. Double bond should have been shared. This is double bond. So look at this. This is alkyl group. This is second alkyl group. This is third alkyl group. If you look at this, there is no alpha carbon here. So we have alkyl substitution. We have alkyl substitution. So this product, by removal of this beta prime, has got three alkyl substitution. So this is Sachs product forming as a major whereas this contains only two alkyl substitutions, so this will be forming as a Hofmann, that is minor product. So whenever we have more than one possible beta hydrogen, the product will be the more stable alkene. Now in some of the reactions may follow Hofmann product. So take this example also. If we have this, so we have two types of beta hydrogen. So let is beta 1, this is beta 2. So two possible products. Removal of beta 1, we have this CH2 double bond, CH, CH double bond, CH, CH2, CH3. The other product is CH2 double bond, CH, CH2, CH double bond, CH, CH3. So if you look at this is alkyl group, this is alkyl group here. But if you look at this is the alkyl group, this is alkene group, alkyl group. So we are talking about alkyl group. So this is Sages product, this is Hofmann product, this is Hofmann product. Now in this particular reaction, removal means we are using alcoholic KOH. As the alcoholic KOH means we are having this normal alkyl bromide with normal base. So reaction should have been the Sages product. But in this reaction, the reaction is forming Hofmann product as a major product, and this is forming as a minor product. So as I have told you earlier, the product which is more stable should be forming as a major product. Now if you look at this, we have a conjugation here. So conjugated alkene is always more stable than non-conjugated alkene. So whenever there is a chances for development of conjugated system, that conjugated system will always be forming as a major product, because the conjugated alkenes is more stable, hence this Hofmann is forming as a major product. Take the same reaction here. We have a benzene substituent CH2, CHI, CH2, CH3. Now we react this with alcoholic KOH. So look at this is beta 1, this is beta 2. Again, two products should be formed. So we have, look at this, double bond CH, CH2, CH3. That is via beta 1. Via beta 2, we have, look at this, EH, CH2, CH double bond CH, CH3. Now look at this. There is an extended conjugation, a double, single, double, single, double, single. So because of this extended conjugation, this is the Hofmann product, but this is forming as a major product. This is Sages. Look at this, we have one alkyl, we have two alkyl, Sages, but this is forming as a minor product. We have one alkyl substitution. So while looking for this product, make sure which alkene is the most stable. Now this is one of the exceptions in which the Hofmann is forming as a major product. There are some other factors in which the Hofmann product also increases. That means if the size of base increases, then the quantity of Hofmann product increases. This is due to steric hindrance. So write down. If the size of base increases, then the percentage of Hoffman elimination increases. एग्जाम्पल मैं आपको दे देता हूँ. We have used this 1-methyl cyclohexane. We have Halides product, we have Hoffman product. So this is Halides product, this is Hoffman product. Now look at this. If the base, we are using this base, alcoholic KOH, then Halides is forming as a major, this is forming as a minor. Now instead of this, we are using this base trimethyl butoxide ion. So look at this, we have 3 methyl groups, so the size of base increases. As the size of base increases, the quantity of Halides decreases. So this is forming as a minor product, this will be forming as a major product. But if you look at it again, we change this from methyl ethyl butoxide ion. So again, the size of ethyl is greater than size of methyl, so base become more sterically hindered. This becomes minor product, this becomes major product. Or if you look at this, we have triethyl CO minus. As the size increases, the quantity of these sizes increases as the quantity of Hoffman increases. So as the size of base increases, the percentage of Hoffman increases due to steric hindrance. As the steric hindrance for in the transition state increases, stability increases, so the quantity of Halides product decreases. So along with this, we have to see the size of base for this elimination product also. So this is elimination bimolecular E2 reaction. So we have considered various factors which governs this E2 reaction, and one more thing that we have to keep in mind, which is very important from stereochemical aspect. So look at this, we have, as we have told you, tertiary iodine is the most reactive for this elimination reaction. Now look at this, we have this tertiary iodide, this is tertiary carbon. So we have, look at this is beta hydrogen. This reacts with alcoholic KOH, which is a strong base. So the product should be, you should have in the product, but this tertiary alkyl iodide does not react here. Though we have a tertiary plus iodide which is most reactive, but this does not react. So this is a very important aspect for this E2 reaction. So during the course of E2 reaction, the transition state has to acquire alkene character. Now alkene character means the carbon should be sp2 hybridized. Now look at this, we have a bridgehead. The bridgehead carbon can never assume planarity. So this is bridgehead carbon. Bridgehead carbon. So bridgehead carbon cannot assume planarity. So since the bridgehead carbon cannot assume planarity, so there is no possibility of double bond formation at bridgehead carbon, so no reaction takes place. Even if you use a much stronger base or a very high temperature, this alkene never forms. The reason is bridgehead carbon cannot assume planarity. So means whenever we have halogen to be removed at the bridgehead system, no reaction takes place, and this is what we call as Braid's rule. So according to Braid's rule, the bridgehead carbon cannot assume planarity and no elimination is possible at the bridgehead system. So this is E2, the stereochemical aspect of E2 reaction. So hopefully that is some of the examples and some of the features and why this E2 reaction takes place. So hopefully you enjoyed the class. Let's meet you again.